good stuff.
No, it was fake.
That's why I wanted to do that.
Fake things with LV.
Okay.
He's not allowed to look. He's not allowed to. Yo,
You know all the countries that the Chinese say? You know all the countries that the Chinese say? Did you like?
Yeah, I know.
Yeah, bro, that's kind of crazy.
I recognize it.
No, I'm applying for something. CSE award.
What is Bangladesh?
I want to know.
Whoa. Yo, you guys exist? Yo, they added the agua too. There's no fish in the water.
There's a lot of them. I'm applying for like people she's asking what should I put in. It's like leadership, academic achievement, and student work, blah blah blah.
Bro, what is this building? Bro, it's
You probably have emails about them. Hold on. Yeah. There's one on Jan 9th.
That's fine. Hey, yo, S1? No, my glasses are fine. It's doing its job. That's
You have to write like an essay or something.
It's doing what it needs to.
Probably just so that not everybody applies.
Yeah. So you can just, and now it's like ADC.
Oh, wait, I need to get back to this. Oh, wait, it's posted. Well, I'm not in the fucking campus right now. You? Yeah, I didn't see the campus. Oh, yeah. They didn't invite anyone else. Oh, wait.
Yeah. It's okay. Yeah.
Oh, you can do that?
Yeah.
Makes sense.
Wait, can you send me the link? Because it's not letting me sign in.
Real?
Because your email. No, but my Google Drive. It's my Google. It's not my. It's not my account.
Bro, I have so many tabs open because I haven't decided my courses. I have stuff open for every course. I got so excited.
Why he died?
You don't understand.
I need to join on my laptop.
So you're just like voltage dividers.
No, it's two bros.
Oh, he's asking me.
What about the labs? Oh,
No, it's four bros.
that's unfortunate.
Six.
No, that's whole guy.
Between like parallel.
No, between the series. Yeah.
What is it?
Go up. No.
All right, guys. Oh, can you hear me?
I'm just saying, so you have 0.
Yeah, I don't want to pull
0
up.
was setting that. 1 is not.
Longer.
So pull up to make it 1.
Hello, hello.
So I have a.
Like, I don't know what memory that is.
So basically, you want.
That's. I guess I do know what inputs are now. Shit, maybe I do.
Do I know it?
Hello, hello.
No, but they're probably
Can
just
you hear me?
Yeah, no, it's like interrupt vector table.
like for real.
Yeah.
It's off this class.
I think the project is with me. Like, that's part of why.
Hello, hello.
Yeah,
Can you
like
hear
I
me?
technically know these words, but
All right, guys.
except I.
If you haven't got a chance, please take a picture of the Google form here. This is just like a form for you to input some of your background. You know, which year are you in? What's your current enrollment of the class? And I know that some of you guys are still on the waiting list. I think we anticipate to have about 10%-ish like turnaround and like changes in the first week or two. So if your waiting number is around like 10-ish, 10, 12-ish, you still have a decent chance to get into the class in the end. And for we are aware that some people want to switch between lab sections. So I think the easiest way to do that is actually find someone who is willing to switch with you from the lab sections that you wanted to take, and then come to us, and then we will make that switch for you with the administrative person, so that you don't lose your seats in the class. So has everyone all take a picture of this? This will be due next Tuesday before the class starts. Sorry, what? All right, so this welcome to the 373 Introduction to the Embedded Systems. This is lecture 1, so we're going to talk about like the course intro and overalls, and hopefully gets to some of the early content of the course. So a little bit of the announcement here. First, the one that we just showed in the beginning, we take the intake surveys about your background and your previous experiences with the embedded systems. And we will have the homework 1 posted soon, and it will be due next Friday. Generally, the homeworks will be due on Fridays. So just get your head up. And we will not have labs this week. The lab 1 is going to be starting next week. In case you haven't checked out the website. So typically we do pre-lab, during the labs, checkoffs, and as well as post-lab. So the pre-labs are usually due before the lab starts. For next week only, the pre-lab is going to be due in lab. We're going to have 2 exams. So the exam dates are set on the 6th of February, as well as on the 13th of the March. All on Fridays, 4:30 to 6:30. The locations are still DBD, but the days will be on these days. Also, if you have any questions, feel free to raise your hands, and then we can answer that to the entire class. Also, make sure you have enrolled in the Grayscope as well as the Piazza. I think the Grayscope is just up today, so after the lecture, you can check if you have access to the Grayscope. For the Piazza, we do aware that sometimes there will be some changes and shuffling in the enrollment. We will try to keep that updated on a daily basis. So every day we're trying to update the list. And if you believe you enroll in the class and did not have access to the Piazza, please send us an email, and then we can figure that out for you. Any questions so far? Okay, perfect. So a little bit on the lecture outline today. First, course overview, which we'll be getting started very soon. And second, we'll give you a quick overview of the STM32 architecture, which will be the microcontrollers that will be used. This STM32 is a family of microcontrollers that are developed by the STM Electronics, which are based on the ARM Cortex-M process course. Oh, sorry. Well, also, before that, we'll talk about what is actually embedded systems. And then if we have time in the end, we'll give you a quick intro to the GPIOs, the general purpose in and out pins, which are the most common pins you will be using and interact in your labs as well as final projects. So with that, I'll get out of the way. First, let me introduce myself. My name is Junyi Zhu. I did my undergrad at University of Washington in electrical engineering and computer engineering. And then I moved on to do a PhD at MIT, EECS department, specifically in computer science. And then after that, I graduated and came here, became assistant professor. And, this is my lab logo. Sensing, Intelligence, and Experiences Lab. We do some pretty cool stuff, so feel free to check out our lab website if you have a chance. Next, I'll quickly introduce some of our lab members, lab instructors, as well as our GSIs and IAs. We're good with a pretty good team this year, and with a lot of helping hand, so you guys should be all covered. First will be our lab instructors. James, you want to say a few words?
Hey everyone, I'm James Carl, so I'm the lab manager for this course. I also teach a couple sections. I actually took this course 15 years ago, so I'm here because I liked it so much I want to come back. But anyways, yeah, I'll see you in the lab. I'm pretty much there all the time, so yeah.
I'm Sam. I'm a senior in CS. I took the class a year ago with Junyi. And I know it can be kind of intimidating going into a big project-based class like this, but this is one of my favorite classes I've ever taken, so you should be really excited you get to take it as well.
Hi, I'm John. I'm a master's in VLSI. I took this class 2 years ago, so quite a while, but this will be my 3rd time teaching, so I'm looking forward to see what you guys do this semester.
Hey, I'm Tasia. I took 373 2 semesters ago, and then I took 473 last semester. They have been super fun classes, and I genuinely think they are kind of the best classes in CE. So, yeah, looking forward to working with you guys.
Hello, my name is Sergey. I'm a second-year PhD student in ECE. My focus area is embedded systems. Got quite a bit of experience in embedded system design, PCB design, shipped a couple of commercial products. And yeah, this class should be pretty fun for a lot of you. I'm pretty excited, looking forward to seeing you in lab, looking forward to seeing the kind of projects you'll be working on.
All right, thank you guys. So if you run into any immediate questions regarding labs and stuff, I think James would be the first one to ask. And chances are a lot of the GSIs and IAs would know a little bit more than me than the lab sessions, lab content. So if you run into any of those questions, feel free, and please do reach out to them first and then reach out to me. All right, so let's show you some of the course goals. Disclaimer here, any course that claims to teach you how to design embedded systems is somewhat misleading because we are not exactly certain on the definition of this technology and how are they continue to evolve. So embedded system as its definition and what it represents is a constantly changing group of technologies. But we will still try our best to just give you some intuitions and show you how to implement some of the embedded systems that we have today, including the hardware and software interfacing. You will also learn to design these with the microcontrollers and design like an entire embedded systems that basically will help you hopefully shape your thinkings on the embedded system software and hardwares, how a specific system interact with the real world based on the real world input and the output on its corresponding designed goals. And then you will also have the opportunity to do design on your own, well, in terms of team, like a non-trivial project, which as your final projects, that involve both hardware and software. Hopefully, at the end, from the combination of the course, which from lectures, labs, and final project, you will have like a foundation knowledge of that will go a long way about how an embedded system, it's what it is, and how it's going to be developing in the end. And hopefully, with the definition of embedded systems constantly evolving, you will still be able to adapt to it based on what we taught in this class. Some of the course prerequisites, 270 and 370s are the ones that listed on my website. So basically, it teach you some of the more fundamentals on the logic designs, as well as introductions to a little bit of the computer architectures from the microprocessor point of view. 280 is something that's nice to have. It teaches you some about like the C programming, which you will be used for a lot of the programming in our courses, or in generally speaking, a lot of hardware codings. But in the end, well, in this class, you will be able to put all these three together and design a working system that actually moves and stuff. And apart from that, not a prerequisite, but it's really good to know some basic electronic circuit stuff, some intuitions about current, voltage, short circuits, if you've never heard about this before. Think twice when you take this class. And some basic designs regarding the resistors, capacitors, maybe voltage dividers, etc. During the lab sections, as well as final project, you will be interacting with some very useful tools from computer engineering, which are oscilloscopes, function generators, as well as voltage supplies. In terms of the class topics, we will have the following topics. First is the Cortex-M4 processor. In this processor, we'll talk about the ISA, the instruction set architecture, basically the command that goes into your processor and then tell each part of the embedded system, each part of the microprocessor what to do with them. And then we will talk about the memory map I/O, MMIO. It's basically the idea of using memory address to talk to the input and output devices. These were including like your common switches, LEDs, as well as some like internal stuff like hardware drivers, hard drives that you don't usually directly interact with, but they are all part of this MMIO interface system. Basically, anything that connects to your microprocessor or microcontrollers is going to be managed by the MMIO system. We'll also talk about interrupts and timers. Basically, this is how we make the processor aware of any of the event that's happening, and then make the whole system to be like event-driven, so that it reacts to things, reacts to the environment input as soon as they happen. We'll also talk about some common data buses and device interfaces, like serial buses that used, for example, internally, as well as some SPI, I2C communication protocol that you use for the interactions between the microprocessor or microcontroller to the external peripherals. External peripherals basically means additional stuff you connect to your microcontroller or microprocessor, like some sensor modules, keyboard, mouses, even screens, etc. We will also work with analog and input and output. You will understand, this is basically how you will understand the real world. The real world, as we know of, is analog, and then in the computer world, as we know of, are 0 and 1s, which is digital. So how do we convert the signals between these two? ADCs, DACs, these will be becoming your best friends for those few weeks. Yep. Any questions on any of the topics so far? No questions? Have you guys all heard about the term? Yes? No? No comment? Okay, we're off of a good start. Okay, a little bit on the additional materials that you'll be quite handy for the class. So generally speaking, embedded systems is about the reading manuals and search online and find answers. Hopefully more than just ask your ChatGPTs, but also actually look into data sheet and menus, as they are like the ground truths of how this sensor or how this module is supposed to work. And these are the two books generally considered as school resources. First is the embedded system with ARM Cortex-M processor, assembly language, and C. So that's the textbook that most of the class material is actually based on. And the second is, the actual menu from the Cortex-M3 and M4 microprocessors, which is the type of microchip you guys are going to work with in the lab sections and in the final project. Next, come up with the most important stuff, the gradings. So this is how the class is going to be graded. Class participation, 4%. How do we calculate this? It's going to be a combination of the in-lecture worksheet. So basically, in some random lectures, we will send out worksheets, and then you fill it out, and then turn it in as you leave the lecture. So in case you couldn't make to all the lectures, we also give you some ways to make it up. So namely, be more active on the piazzas, not just asking a bunch of questions, but actually answering questions from your peer members of class. So we will take that into consideration for the class participation as well. So this class is going to be one of the classes that everyone helping each other, because you will know that will be super handy when the final project comes and you all put all-nighters together. So that's how the class bounds. And homework, we're going to have about the homework take about like 10% or 9% to be more specific. We used to have higher percentage for the homework, but nowadays, as you all know, homework might not be as a representative for your actual performances. So we actually cut down some of the weights on that. The labs, we still hold a pretty decent amount of in the lab sections. We have in total 7 labs. They take up until 24% of the class, actually a pretty big amount. So it will be graded based on your basically the pre, during, and the post lab checkoffs. And I think as long as you put in the time and don't afraid to ask questions to our great GSIs, IAs, as well as lab instructors, most people do just all right on the lab sections. And 2 midterms, each 15%. That would be, well, no other way to put it. It's going to be one of the big part that separates the grade. But we will talk about that later once we go to that. But 15% each. And we also have additional to, well, different from most of the classes you took so far, we also give you presentation scores, 5%. So what it is during the presentation, you will have, during the last 2 weeks, 3 weeks of the lecture, we'll ask each of you to pick one of the embedded system topics and do like a presentation to the class in the team of 4 as your final project groups. And then we will grade that just based on how clear the delivery is and how well the content provided, etc. And the final project, most important one, almost 30% of the entire class. This is going to be taking up the most of the time. And about the last month of the class, you will be expected to put in all your effort into this part. Generally, the class median should be like a high B plus / A minus. So yeah, just be aware. And if you, we have complaints from other peers that we migrated too loose last time I teach this class. So this time, if you don't perform well, you will fail the class. Sorry about that, but yeah. Any questions? All good? Yeah.
Are the groups for the written presentations assigned or verified?
Good question. So let me actually go to here. Just give you a little bit more information on this. We will have a team formation event, which happens on the 13th of February from 4:30 to 6:30. And this is where you're going to find your teammates. We try to hold the team formation event to be more like organic. So you come and then we before this event you submit like a sheet indicating which are the interested areas or ideas you want to work on, and then we kind of divide it into like small clusters of people who are interested in similar stuff, and then hopefully most of the teams just formed organically, which they actually did in the past years. And if in the end we still have a few leftover friends, we will help them make friends and then form the team. Yep. We will still ask you to come to the event, but feel free to start making forming teams even before the event. Yeah, but we do enforce 4-people team because we have a lot of folks here, and we are having quite limited lab space. So we kindly ask you to, form a team of 4, and then so that we have enough workstations for you guys during the final project period. Any other questions? No? Okay. Cool. And there's no other way to put it. It's going to be a pretty significant time commitment for the class. Just give you some of the historic data from the previous folks. But on average, you should expecting to have like about 12 hours per week before the final project, and about 15 to 18 hours per week, even 20 hours per week for the final project periods. For the 3 days in front of the final the final demo expo, it's probably going to be 1 or 2 all-nighters. So, not trying to scare you, but that's just how it is in the past years. Any questions? Any concerns? Yeah. the final project topics, we try to have it to be pretty open-ended. Trying to have it to be pretty open-minded, but we do ask you to be, well, first it has to be the embedded system that you're building. And we're trying to do what we call bean counting. So based on how many people you have in your team, you're supposed to have like amount of the hardwares you added to the system. So if you're trying to get away with the final project with a bunch of super fancy software skills and computer vision stuff, that might not be the course for you. So we do ask you to adding actual sensing modules or peripherals, meaning different types of devices that connects to your embedded system or connect to your microcontrollers to work as a whole. Yeah. So pretty open-ended, but it would be we were making it to be more, I guess, hardware focused, a balance. But now that everyone's doing hardware, everyone's doing software, so it's to most of you guys, it's going to be a very much hardware balance focused. Any other questions? Okay, cool. And if you haven't got a chance to see the class website, we updated everything, and the most important pages. Let me actually go to the actual website. So here's the website. You will see that the most relevant to you guys, and you will frequently be checking, is first the class schedule. Basically, with each topics, what topics going to be covered for that lecture. And down here, we will put the lecture recordings as well as the lecture slides. We'll try to put the lecture slides before the class, so that in case you want to do some notes on the lecture slides, feel free to download that before. We will hide the worksheet from the pre-released slides. So if you want to use that as a get around for the, forget about it. Another important thing is, one more thing. So this might be a lively and dynamic Google Sheet. So if there are some changes to the schedule as we go with the class, it's totally possible. But we will make announcement on the Piazza, not just silently update this without telling you guys. Another important thing to look at is the assignment. So for those who came in late, who didn't scan the QR code, no worries, we put the links here as well. So here is where we're gonna post the assignments, homeworks, labs, not labs, homeworks, as well as some of these additional, practice exams, as well as some project-related documents here, as we go along with the class. Another important tabs to check out is labs. I think so. As we go, the James and our GSI IAs, they're going to start putting their time commitment to the lab calendar, so that you know which lab section is ongoing and what are the open lab sections, which potentially can serve as like office hours from our GSI IA and lab instructors. And for the lab assignment, you can already start looking at them on the website as well, in case you want to start early. But I think you guys don't have the hardware kit, so yeah. Any questions on the class website? Yeah?
So where do we find the pre-lab? Are those in the...
Oh yeah, the pre-labs will be in the inside of these lab folders. So if you click on one of, just do like lab 2, you should see a bunch of informations you need for the lab, which contains the pre-lab and all the requirement checkoffs. Good question. Any other questions? Yeah.
And this week, when is the pre-lab due? Like for the next?
It would be during the lab sections that you assigned. So this will be the only exceptions. So the pre-lab for the next week will be due during the lab sections. So. All right, any other questions? Okay, perfect. Also, while we added this topic, if you go to the staff, we also listed our basic information here. This is my office number, and 12 p.m. to 1 p.m. on Wednesday, either in person or over Zoom, will be my office hours. Feel free to email us to schedule any additional office hours outside of the normal assigned ones if you need, but by default, this will be available. Okay, perfect. So, with all that, what do you get out of this course? Well, before this class, I think most of you guys have been studying engineering, or at least EECS related topics in abstracts. This lecture would be probably for a lot of you guys the first time to actually synthesize all these knowledge and solve real-world problems. And what that means is you don't do your, well, the big challenge for you is no longer just fitting and calculating on paper for your homework or exams. You're actually going to touch on the hardware and make things move around and interact with the world. So by the end of the 373, you should have your first definitive step to become a real engineer. So pretty exciting. And this course, considered by a lot of students as well as industry folks, are pretty transformative. All right, now that we get off, now that we finished the course overview, let's dive into the second topic. What is actually embedded system? Any questions before this? Any questions regarding the course overview, structure, logistics? Okay, perfect. Yeah, go ahead. Yeah. Okay. So the lab members are going to go prepare some very important stuff in there. All right. Obviously, embedded systems are everywhere. Let me just give you some examples. For example, like during the transportations, oftentimes these are, you can say they're like computers without screens, right? They're like human-facing interfaces. And in like modern cars, we have more than 100 different microcontrollers in them. These are considered as embedded systems. As well as if you look at like some medical domains, medical devices, they also have screens, but they build for like very specific tasks. For example, your like EEG monitoring or EOG monitoring during the ICUs, etc., and MRI device, etc. These are all considered as embedded systems. During home and office, printers, microwave, Wi-Fi routers, as well as a lot of the consumer electronics, like screens or cameras, etc. Give you a specific example here. This is a Nest thermostat, which I think a product by Google, and which you see from this thing just from the outside. What does it have? Have any of you guys owned one of these thermostats? Okay, perfect. Bunch of you guys. So what did it have on the surface? It has a screen to just show you information. It also have a rotary encoder that basically allow you to input into this system. But underneath it is a bunch of stuff actually. So this is the PCB board, printed circuit board, inside of this thermostat. What's included here? Well, first we have Cortex-based microcontrollers. This is very similar, a little bit more capable, but very similar to the microprocessor you're going to use for the labs and your final project. Apart from that, you also have a bunch of other things, like Wi-Fi modules, other wireless transformation flash memories, as well as some motion sensors and power management for additional life cycle for each of the charge or batteries. Any ideas why this small system that only controls the temperature and the humidity requires all these additional components in there? Oh, I forgot. It also have like a temperature sensor inside. Bummer. But any ideas why do they need all these stuff on a simple thermostat controller? Yeah. Mm-hmm. Yeah, exactly. So just like you said, although it only controls the thermal from which you see it, but underneath it requires, or it's capable of a lot of other smart things. So basically, it will be able to save energies by, like you said, if you don't detect the human presence for a long time, it might, drop the temperature setting. Or if you guys noticed, every time when you're walking past it, the LCD screen lights up. That's also done by the detection of the motion sensor. For the wireless communication, this is so that you don't have to walk towards it. You don't have to be in the room to control it. You can control it, from your cell phone, halfway across the world. So these are all the additional functions that goes into one, like very small, looking small embedded systems, but actually have a lot of capability. And to just give you a but although with all those components compact here, roughly the sensing component cost, or what they call BOM cost, bill of materials, it's about like $50-ish, give or take. But of course, they sell for about $280, almost $300, and that is how a lot of you guys gonna make your paycheck. So, a quick detour from like a specific, like example we just give you. What's the driving force behind the technology innovation, and how do we get here from previously, moon landing? Like for example, if you just look at that small microcontroller chip, microprocessor chip there, it has more computing powers than people did the moon landing back in the 60s. So what have we come from there to now, and how we're able to afford it and have this concept of embedded system? You guys probably all see these type of figures from somewhere, so I will go through it fast. But an index people sometimes consider is called PPC, people per computer. So basically from early 60s, it's going to be probably one computer per department or even per university, and then all the way comes down to now every one of us owns more than one computer. Your laptops, your smartphones, your tablet, etc. We also have significantly smaller and smaller, from the sizes perspective, so that we are able to physically have more of them in the limited space that we have, from the apartment space to hold these personal computers to now the pockets and wrist, and probably pretty soon on your face, some of these computing devices. Another thing is also the price, the computing price, to be more specific. The amount of computing you're able to get per dollar has also dropped, substantially, exponentially in the past few decades. So you all heard about this, a new computer class every decade, just based on all these innovations and the size shrinking and everything. And it's actually a pretty ongoing discussion and explorations on what's the new class of the computers now and will be in the 2020s and 2030s. A few other, actually, this one. A few other interesting trends you might notice. So this is the trend in the speed of wired and wireless communications. Normally, people consider wired communication to be much more stable and way faster than wireless communication. But nowadays, if you look at these charts, they're getting closer and closer, and probably going to be I'm not sure about actually going to be surpass the wired communication just because of physics, but they're going to be very, very similar to each other. And just imagine, when that happens, all type of new computing devices, what are the new small devices that can be available to us. just based on this innovation. Another big thing that's currently happening is the battery technology, largely driven by the EV industry. They're trying to make more energies into per square feet, or basically per volume, and then make them smaller and smaller. This is another current driving force for a lot of these computing platforms. So, a question for you here is, what's next? Let's do like a quick brainstorm on this one. What do you think would be the next computing device or computing platform after the smartphone? Or maybe it's already there. It's one of the devices you already have. Let's spend 2 minutes on this. A few questions to start to just get you started. What's the size of the device going to be? How many of these are out there? And how much it's supposed to cost? And how are they controlled, etc. Let's talk to your neighbors for about 2 minutes.
Something you don't have to because the inconvenience of the phone is like having a timer. So like you should just
I
be
think
able to.
phones stay. I think phones are the future. I don't think we'll find another, because there have been become like they've tried. What? LG smartphone. Well, I was just gonna say, I think that I feel like different form factors have been tried before and without much success. Think about like the whole VR boom and bust.
I think you can have like holographs. I feel like holograph would be so convenient. Like you're going to workshop, you can do your homework like this.
Always. Do they see this font here? Yeah. That'd be a hell of a distraction.
Yeah, and that's what all of technology is.
Can you imagine the number of people that'd be walking into poles?
Yeah, and people already walk into phones.
Yeah, but not to the same degree as what you're proposing.
Well, phones are distractions too. I actually do think the more pervasive it is, the more people are going to get it. And it's going to cost for now, and then it'll drop really quick once the novelty is gone.
I just know one of the creators.
Good relief.
I recognize it. I don't know why.
Also, the devices
Would it be like
owned by a significant market.
Yeah, no one. Okay, it never works.
I think it could be like
Alexa, do my best.
Yeah, they're gonna switch your eyes. You can occup
Like a whole new sign language or like
yeah, like whatever takes
Yeah, cyberpunk.
like head nod control.
you could like conduct a virtual orchestra.
I wish
Yeah, it's not I don't want to.
All right. All right. Who wants to share? Hate to break off.
Okay, so you have to think.
All right. All right. Who wants to share their thoughts? Yeah.
Earlier with glasses, but also just there's band or something.
Yeah. So like a lot of the nowadays passive objects just lying on the table can be the next computing devices or platforms, right?
Yeah.
Yeah. Very good thought. And any other? Yeah.
Maybe not like this decade or maybe next, devices that are embedded in your own body, for credit card too. Like have that inside card.
Mm-hmm. So stuff inside of you, more or less. Yes, there are some patients already took that step, and you're in. Yeah, very interesting stuff. There's a community called Augmented Human. You should check that out. Yeah. Any other thoughts? Okay. Well, one possible answers, which is the answers that coming from our embedded system introduction teams. Obviously, it's some type of mobile sensing and computing devices without the traditional user interfaces, meaning without keyboards, without mouse input. That was much more smaller, and that's stay connected to the internet, wireless, cloud computing, etc. That just people carrying around or sitting there waiting for any of the triggers from human needs to be interact. So sounds pretty much like IoT, right? Internet of Things, maybe, but nevertheless, I think even all the potential answers that we have, which are two answers, they all pointed to a future where the embedded system will play a big part of it as the next wave of computing. So some future readings on this topic. This is Professor Gregory about. He used to be at Georgia Tech. He moved to Northeastern a few years ago. He's one of the, I think, one of the pioneers in the field of IoTs and in the ACM IMWIT community. But even with, But in case you didn't notice, I haven't really answered the first question I brought up with. So, what is embedded system, right? I show you the trend, but are they all embedded systems, or are they, more general purpose computers? There are a few different ways to define an embedded system. One of the good ones, one of the ones that we like to do is based on the purpose. So whether this device is more for like general computing versus a very specific applications. For example, if we compare these two, by the way, general computing will be computers, application specific will be embedded system, in case that was not obvious. Considering like a gaming PC versus a gaming console, you can do a bunch of stuff from the gaming PC. First, the cost. The cost of gaming PC is usually higher than the gaming console. It's usually harder to configure because all the component that requires for it to fully function. Have you ever done like a DIY assembly of yourself? You might also need to decide which type of operating systems, which type of RAMs, and all that to put together in order to have it fully function. But for the game console, it's pretty much it's much easier to set up and use. And usually, gaming PCs tends to be like heavier, larger, consume more powers, while the gaming consoles are smaller, lighter, and usually less power consuming. And more on this, the gaming PC, being a PC, it's pretty general purpose. It's optimized for gaming, but you can also use it to do a lot of other stuff, like just watching videos, conference calls, use your deep learning, file your texts, and all that. But the gaming console, you can only use it to play games on it. And depends on which version you have, you might not be able to play some games. Depends if you have a PSP or Xbox. So just give you like some summaries here. The embedded systems usually is about making trade-off and optimizations that for a specific application. So just look at these two. It's usually cheaper, but it's usually easier to set up. But like on the other side, the general computing, although it's harder to set up, it's also give you more freedoms on swapping stuff and keep upgrading, which are usually something not that obvious on embedded systems. So, rule of thumb, general purpose versus application specific, as well as more complicated in terms of setup, power consumption, all things considered, and versus more straightforward, which is easier to set up, but also doesn't have as much as configurations as you might need. Does this definition satisfy you? Any questions? Any other thoughts? Yeah.
So, as far as I understand, most like microcontrollers, for example, are for general purpose. Does that definition still hold here? In that case, or just like a general purpose microcontroller?
That's a very good question. So the question is around if. So when we talk about STM32, a specific type of chip, it's usually that would neither be considered as a general purpose computer or a embedded system as a whole. It's a part of embedded system, or it could be, in this case, a part of an embedded system. So what a end product will look like is you have that core, and that core is hard-coded or it's coded to do very specific things. So that although at the beginning you're able to program what kind of things that you want to do with this core, but with a finished product, usually it's very hard for you to do additional modifications to that. Any other questions? Okay. All right, then I have a question for you. Is mobile phone an embedded system? That's 30 seconds, and whoever come up with the answer, just raise your hand and share with the class.
Because earlier it did two things and now it does everything.
Yes.
Go pick some.
Modern phone has direct parallels to pretty much every part of a general purpose computer.
Okay, any thoughts? Anyone?
They're really good diagrams. It's like to think of like, oh, these are all like, I guess my diagram
Yeah.
like it is. You know?
And why is that? Very good. So if I may ask further, what year do you think a phone began, moving away from embedded system to a general purpose computer? Any guesses? Do you have an answer? Or anyone else can also jump in. Which year? Yeah. 2007? Yeah, pretty much. 2007, 2008-ish. That's, if we have to pick a year, that's pretty much the year that's going to be defined as, where it moves from an embedded system to a general purpose computer. And why is that? Well, that happens to be the time the Apple Store, the App Store opened, where the developers are able to just program your own applications on this device, mobile device that's previously an embedded system. And then, yeah, you get the idea. Anyone satisfied with the? Okay, how about another one? How about autonomous vehicles? Anyone? Just raise your hand if you have a. Is this a embedded system? Anyone? Yep.
What? I would say it's probably like at least a couple years ago it was like still more of an embedded system because it like all the apps it has are inbuilt into the like it has GPS but you can't just play games on your car, I think.
That's very good. Yes. So, just like you said, although it has all kinds of complicated systems, oftentimes more computing powers than most of you guys have your gaming PCs probably, but it is still be considered as an embedded system because it's all these sensors, all these computational power was aiming for one or like a few very specific applications. Driving the car and trying to keep you comfortable, if it can. So, how about this one? What about an SD card? Is this an embedded system?
I'm also just, you know that this is sort of more my background.
I'm definitely.
Okay. Yeah.
Oh, I was anyway like. Anyway.
I would say yes.
I didn't know that, but that makes sense.
Yeah. It's a very, very, very
You
low
cannot read
volume.
data yourself, though. Can you read data yourself? You can't.
Yes, it's an embedded.
All right. Anyone? Anyone want to make a guess or yeah? Okay, so we have one answer here. Say it's not a computer embedded system because it only stores 0 and 1s, right? That's a good thing. Good thinking. Any other counterpoints? Yeah?
I would say it is an embedded system that has a little flash controller that manages shift cells and providing an interface with them that's not just the raw flash.
Did you check the slides next to
No.
this? Okay. Okay, nice. Okay, very nice. So this is actually a very tricky one. So it is, sorry about that, it is actually a embedded system. And the reason for that is pretty much like you said. So inside of this, most of the memory systems are not reliable. So it often requires additional like a controlling chip inside to make sanity checks and make sure data comes in at the right format, stored in optimized locations, etc. So it has this small embedded controller in every one of these flash devices, actually. So we're still good? Okay, cool. So let me just show you a bunch of other textbook definitions. You can read it after class, but basically, also from Wikipedia. But basically, these things all have their limits because, as we mentioned before, the embedded systems are pretty a very dynamic thing. But like general rule of thumb, it's a very specific application defined devices as opposed to like a general computing, and as well as it's usually reactive to what's happening, meaning it's like real time rather than something sitting there waiting to be, programmed or wake up, etc. So, key takeaway from the embedded system definition introduction here is, a lot of these technology and market forces are driving the involving of the computing devices, and these embedded systems usually embed new computing devices that's previously not possible. They usually use those to make specific application-specific devices. And with more computational powers being able to get onto the embedded system level, we are able to, enable more possible applications. And while there are no precise definition of embedded system, but you should be able to see, identify one when you see one. And please feel free to come up with your own definitions after this course and share with us so that we can potentially update the class lectures in the future semesters. Cool. Oops. All right, so that's the topic around the embedded system definitions. Next, we're going to go to the STM architecture overview, which is the type of microprocessors you will be using for the labs. And also give you a little heads up, this is a very high-level understanding of the Cortex-M4 architecture. We will focus on what the components do and how they fit together, not yet on how they actually work. So if any of these feels confusing to you, it's okay. We will dive more deeply and more specifically to each of these topics in the later lectures. You guys probably don't have it yet, but this is your lab development kit, and this is the board you will be interacting with. And the microcontroller, the ARM Cortex-M microcontroller, is that one black IC chip in the center. And give you a quick, simplified Cortex-M4 architecture view. There you go. And if you should all took 370 before. During that lecture, you should talk mainly about what's inside of this circle, which is the processor core. And in this course, we're going to basically focus on everything else apart from this. Well, we're going to talk about different types of memories, SRAM, flash memories, different type of memory interfaces as well. We're going to talk about different memory controllers, as well as all these interconnecting interfaces inside of this microprocessor. naming all the buses. So in our Cortex M4 architecture, all these buses are 32-bit, and the buses are methods to sending like large amount of data throughout the system. These are usually tend to be super high-speed buses. Just to give you a little quick view, if you remember from the previous courses, or if you know something beforehand, this is what like a bus, basic parallel bus looks like. Basically, it's a bunch of D flip-flops and plus a clock that that tells you when to look at all the data on the data buses, and then register that to wherever you assign it to be. All these are in parallel. We do have like some serial ones, but we will talk about that later. We also have different type of buses. We have like high performance ones versus normal peripheral ones, which usually are for high speed data versus lower speed data. All these are pretty fast, but you know there's still something that stands for higher priorities when you're connecting different peripherals or external devices to your core or to your microcontroller. And we'll talk about different type of peripherals. The APB ones that usually communicates through various different communication protocols here. It's usually considered to be used for like external devices such as like keyboards or like more latency toleranced devices. You might think your keyboard is pretty responsive, but compared to other more higher speed required devices, this is actually okay-ish. The high performance ones will usually go through the GPIOs, ADC, which is the type of channels that cover the analog signal from the real world to digital signals. So these ones usually are like more high performance critical components, such as such as you'll be used for like some immediate event that needs to be triggered a response from your embedded system. Again, we will talk more about this later. We'll also talk about like interrupt, as we probably remember from the previous slides. But from like an architecture point of view, the interrupts coming, it usually stops the normal process of your instructions and then to do other tasks. It's like a lot of things can trigger a interrupt. For example, user press a button or some lights, LED lights, like some alarm lights light up. Those can all serve as the interrupts to the system. Give you like a example of how things flow in this architecture. Let's say that if we want to load the content of the R1 into the register R0, and here is where the instruction comes from. You program it and then send it to your core, and core basically takes the data and fetch it, and then the core will decode the data, and then put it into wherever and then load that content to the register 0, which is here, register bank. And say if we want to store data, say if we want to store the data into the register and store the data in the register R0 into the memory address R2. So what can happen is, obviously you have the instruction coming in first, and then again fetch the instructions, and then the core will decode it, and then send the data to where it's supposed to be. In this case, the timer. How is things holding up for everyone so far? how things flowing around in this architecture, and just give you a quick overview of how each of these components are supposed to be doing. All good so far? Yep.
Wait, can I ask? I thought we were just writing to a register. Why did it go to the?
Oh, that's not obvious here. It's just in your actual coding. That register's value is it needs to be sent to the timer in the end. It's not obvious from just. It's just that memory address belongs to the timer. So. But yeah. So holding up, this is the actual block diagram. But if you look closely, you will notice that these are actually very much similar to what we just showed as a simplified one. It's still good to know all these stuff if you want to look at the complete data sheet to know exactly which components connects to which. But there you go, same stuff. And there's a second half. So, but after this course, you should be able to read this entire data sheet, no problem. Okay, any questions so far on that's probably on the simplified architecture? We good? Okay. Perfect. So next, we're going to talk about the GPIO. A quick intro here. GPIO stands for General Purpose Input and Output Pins. So the similar on the left, this STM integrated circuit. It's a very similar chip you're going to have on your lab kit. So if you take this chip and then put into this black package, usually squares, and then you will become an IC that you usually interact with, which looks like what you actually see on your board. And inside of this, they have those little small wire bonds on them, so that they fit in each of the same footprints there. And these wires coming out, the little footprints coming out, the pins are the ones that you use to solder onto your PCB board. How many of you haven't done solder before? Haven't? Have you never heard about the word soldering, or you haven't soldered a thing before? Okay, perfect. Only a few, so you guys will be fine. And then, basically you have this thing that's like smaller, and then with a little bit wire bonding to the outside, and then that goes onto the actual board. And on the actual board, those, let's see if you can. Those black ones where you actually stick the wires in, those ones are generally the GPIO pins, general purpose in and out. They usually directly connect to some these footprints that you use to solder, and then they got directly connects to the actual IC, like the actual core inside of this IC chip. All good? Okay. And from like a Cortex architecture perspective, this is where all the GPIO pins stayed on this architecture, and they pretty much send in and store 0 and 1s, and yeah, you can think of them to just turn on and off in LEDs. And then all those all those data are usually going to be fetched into the registers. Usually, we'll talk about it in more detail, but like GPIOs usually connects directly to the registers. Do you guys remember what the register is? Yes? No? Okay. So pretty much a bunch of deep flip-flops and a clock, similar to the buses that we talk about. They use underlying very similar hardwares. And in our board, there are 32 of them because it's a 32-bit system. And it's used to send the data in and pull it out. Depends on how you configure it. And in the datasheet, it will basically tell you where the address of these registers. So for example, in a command here, it tells you to store in the register 0, and then basically do that. And if you want to load the data from register 0, that's the command you use, and then you will load that data from the register and then store that into a specific memory address in your system. So the key thing here is you need to know the address, both for especially for where the data is sending to, as well as where the data is stored at. So you will soon learn later that the address is probably the only thing you know across the entire Cortex architecture, where things are stored. Everything, it just have an address to it. And then if you give it the correct address, it will be stored at the correct component or correct location inside of the entire architecture. All these things connects to this have its own address. It doesn't tell you what it is. You should only just look on, a specific address will corresponding to, say, the memory interfaces or like SRAM. All this, they just have the unique address, and you use that to interact with all the components here. And yeah, if you want to know any specific address, go check the data sheet, and you will know exactly which address you need to, write any of these into. And then if we give you like a simplified output pings, basically, you have a data coming, go to the D side of D flip-flop, and then based on the clock, you have one positive raise, and then the data got fetched onto the output side. This is for the like a simplified output version. And if it's the input, pretty similar. I just swap the pings there on the D flip-flop, and then data sent from the ping, physical ping, usually through the actual through the real world, so to speak. It can be connected to external sensor modules that senses, say, temperature, humidity, or human presence, and then that data got constantly sending towards the GPIO pings, and then goes through the high performance buses to aware the core. Any questions so far? Okay, cool. And give you like a quick example of this. Have you guys used this website before? Fallstat. It's like a online circuit generator, and you can use it to do some pretty easy circuit simulating the behaviors and stuff. Let me show you an example of this. So here is a very simple example, the GPIO here. So in case we have like two GPIOs here, it's very easy. It's probably as simple as it gets. Pretty much it gets the input, and then the input connects to a switch, and then internally it goes through something, but we just simplify it with one wire, and then goes to another GPIO, which is the output, and then that lights up an LED. So if you want to work with this, just click on it, and then you have your LED light up. Okay, no impression at all? This is like the hello world moment of embedded system for you guys. So yeah. You will do something similar to this in your lab sections, so you can actually see a light up instead of me just click on a bunch of buttons. But you will notice that if you look closely, bottom here, it have a thing that's rolling around, which usually connects to a clock, a concept you will soon be familiar with. And then based on, okay, so based on the input or any changes that happens in the input side, you will see the signal on the bottom there changes at each of the node. That's how you're gonna simulate like some simple circuits inside of the software. We will be using this tool for some of the later as well to just show you different type of circuits and how they work in principle, so that we don't have to bring an actual hardware here. Any questions on this Hello World circuit? Okay, let me just point out something real quick. You notice that there is something connected to the LEDs. That's called a resistor. You guys should always check what's the maximum load the LEDs you have can take, either on the voltage or on the current, and then make sure you don't blow up some stuff unintentionally. And as we speak, so let me do this. All right. So this will be something a little bit more complicated. You know, we have basically two things that's connected to a output, and then based on so this will be like a simplified version of a GPIO. This is as a combination of these two. So this circuit together, we will be able to in having both input and output capabilities inside of this GPIOs. Just depends on which one got triggered on this pull and push and pull output. This will be like this control here will be determining whether this GPIO pin is being set as input or output, and that will be deciding whether it's outputting or taking input constantly, which is why it's called general input and output. Any questions so far? Okay, cool. So those would be like a very quick introduction to the GPIO pins, which is, you know, a very simplified, but just imagine this thing have 32 of them, and that gives you one GPIO, 32-bit GPIO. In case you want some of the circuit reviews, we have some cool, materials here to check out, some YouTube videos. Another source I recommend, which I will post in the Piazza, is a website called SparkFun, which have some pretty good explanations on how some of these circuit basics, voltage, dividers, current, how they drive through the circuit, etc. So, give you a quick recap of the lecture today. We talk about the general course overview. If you have any questions, feel free to raise in the Piazza or directly email any of the teaching teams. And we talk about some of the technologies and forces that's being driven the embedded system. And we try to give you a definition of the embedded system while it's being pretty dynamic and evolving. And you should be able to identify these things when you see one after this class. Next, we give like a very high-level architecture overview over the STM32 M4 Cortex that you're going to be working with in the lab and in the final project, as well as the starting of the GPIOs. And for you guys, please take the next days to give like a quick refresh on some of the circuit basics. If you took that from 215 or whichever courses you had, if you never took on 215s and you never heard about the term like oscilloscopes, capacitors, voltage divider, transistors, now is a good moment to take some of these materials and learn some basics of that. Otherwise, it's going to be pretty hard for you to stay on track for the labs later. And next lectures, we're going to talk about ISAs, the instruction set architecture, assemblies, as well as the application binary interface. So not any yet, but basically just give you like a key goal for the next weeks to just understand how the code, basically the code you write, got converted into the instruction code, and how that and the memory and the register work together. Basically, how the microcontroller interacting with the outside of this board.